Alright, let's go ahead and finish fleshing out that list of targets for a U substitution. You'll recall we've already filled in so far stuff in parentheses, stuff under a radical, which was really just a subset of stuff in parentheses, stuff in a denominator. I guess technically we've got a theme about parentheses. This isn't really going to change that, but it's boring just to say look for parentheses. In particular, because this last move very frequently, when you see it like written in a textbook or on a test paper or something, doesn't look like there are any parentheses around. So, and this one is near and dear to my heart. You may recall the exponential function is my boy, and I want to bring him up wherever I can. So stuff in an exponent is a really common target for substitutions as well. Kind of coming back to that whole, you generally don't mess with exponential functions when you do calculus to them. They just kind of pop back at you more or less unaffected. So to see this in action, I do want to play around with an example where it feels really tempting just to ignore having to do any extra stuff. So let's do that guy. The indefinite integral of e to the 6x dx. It's really tempting because, again, the exponential function is so nice just to write e to the 6x plus c, call it a day. That's not 100% accurate. It's actually 100% inaccurate, but whatever. Remember, we can only use our bestest friend formulas like the antiderivative of e to the u is e to the u if we have an exact match. We don't have an exact match. So we're making a teeny tiny u substitution. It's not terribly involved, but yeah, we want e to the, as you said, we want 6x for our u in this instance. The du will be 6dx. Hopefully you get the idea at this point. Let's get the dx by itself, because we don't really have much extra stuff. That turns this into e to the u times 1/6 du. Pull the 1/6 out front. Like we've said, the antiderivative of e to the u is itself. So we have 1/6 e to the 6x plus c. And done. So we still get the exponential back, but we do need to keep that stuff in mind, because don't overlook it. That's that's not good. All right, so I want to take a look at one more example of an exponential, and then I want to visit some other stuff real quick. So hang on. I missed the button. All right, so let's take a look at something that's not just a constant times x floating around in our exponent. So we have xe to the negative x squared dx. Oddly enough, without this x right here, this problem becomes substantially more of a pain, as in it's beyond the scope of us, being able to do it in Math 115. Anyway, so as it's written though, we don't have an exact match here. Let's call that our u. U is negative x squared. Du, like we do, is negative 2x dx. And now, that's why there's this x floating around, because Professor Carroll likes us and wants us to be able to work this out. So divide over the negative 2, negative 1/2 du is x dx. And again, if you need to rewrite this and pull the x in the back, that's fine. Like I said, I've been at this for a really long time at this point in my life. So anyway, so we have e to the u times negative 1/2 du. Negative 1/2 is a constant. He can be conveniently dragged out front. So negative 1/2 e to the u plus c. Undo our substitution. Negative 1/2 e to the, not negative 2x. Where did I get that? Don't. He's a silly man. Don't listen to him. That's a much more sensible man. Listen to that one. All right. So negative 1/2 e to the negative x squared plus c. All right. So that's the exponential function. Do remember you could use this with non-e exponentials if one of them happens to come up. The formula just has that extra piece that I've mentioned before in it, so keep that in mind. So this next guy doesn't feature any exponentials, so you might be wondering why Professor Carroll is bringing him up. You'll see. Yeah, this feels kind of like a throwback to the last set of videos with this grab the denominator thing. Feel free to try. That's okay. Call u 1 plus x to the 4th. You're going to run into a bit of a problem, though, because the du you need there will have an x cubed. I didn't give you one, and that's not a typo. That's actually just supposed to be an x. So, ruh-roh. All right. As it turns out, we've got to be a little sneaky with this, and we've got to bring up something that we've only kind of touched on a few times in the course, but it does appear in the homework, so I want to make sure you're prepped. Here's the way I'm going to do this. I'm going to call my u x squared. This feels a little weird. It's okay. So that means this thing here I'm actually going to be able to write as 1 plus x squared, and then that last term is itself squared. That gives us the benefit of being able to nuke this thing up here, though, because our du is 2x dx, the usual song and dance, divided by 2. And it may not be immediately clear why I'm doing this. Bear with me. It'll make sense, to some degree in a moment. All right, so I'm going to go ahead and write that 1/2 out front. Hopefully, with enough examples under our belts at this point, you're okay with not having 1/2 du in the back. Anywho, so now, so that's what we'd end up with after we execute that substitution. And you might be saying to yourself at this point, that doesn't really look any better than what we started with. I mean, I guess we got rid of the numerator, but it's still not something that might just jumps out at us as one of our bestest friend formulas. It's not, but we've seen this formula before. As it turns out, we have seen a function whose derivative is 1 over 1 plus u squared. We just haven't had to work with it that much. It's actually the inverse tangent function that would have this as a derivative, which means that our antiderivative, or indefinite integral, would be inverse tangent of u plus c. So you may be wondering why I'm not just getting happy on this and plugging in, the u substitution. When we were talking about the inverse trig functions before, I didn't really have time. I had to bite my tongue. I really despise this notation for the inverse trig functions. I think it's misleading because most of the time when we write tangent to a power, we kind of mean multiple copies of tangent of u multiplied together, except here you're supposed to know it's an inverse. I actually prefer to write this using the phrase arctan instead, so that's also acceptable. So I would normally write this like so. Arctangent instead of inverse tangent. I'm okay with either one if you prefer this. I just really, really don't. I just didn't have time to spew my venom over that notation when we were talking about them before. So, yeah, I like arctangent. I think it sounds cooler to say. But all right. So that's the thing that we would need as an indefinite integral for this thing as it's written. So if you need to at this point, feel free to go back and grab that formula sheet with the derivatives of the inverse trig functions, because like I said, we're not gonna toss them on to the bestest friend, but you kind of need them. All right, so I've got one last example I want to take a look at. It's going to involve another inverse trig function. Not to be too much of a spoiler, but yeah, let's clear this board off. All right, last one. So yeah, again, it's kind of tricky and it's not immediately apparent how you would see this. Having that list of trig function, inverse trig derivative rules might kind of help, but it's still a little bit tricky to see. What I'm going to do here is take that 9x squared that you initially saw written and do this to it. It's 3x quantity squared, right? So you can check that. Let's call that my u. So u is 3x. Unsurprisingly, du is 3dx. 1/3 du is just dx. And then that turns this thing into, all the 1/3 out front, like you do, 1 over the square root of 1 minus u squared du. Again, if you had the 1/3 back here, that's okay. It's, I get it. All right. Again, with most of what we've done this semester, I can see where this would be challenging. The good news is, if you've got that list of inverse trig derivative formulas sitting there, yeah, that's the derivative of the inverse sine, or what I'm going to call arcsine function at this point. So, again, you have no idea how much it hurt me not to write arcsine, arctangent when we were doing this stuff before. Anyway, so, all right, so, oops, I shouldn't have put a box around that. I've been a naughty professor. Okay, so Get rid of that, because what have I not done? I haven't put my expression for x back in here. Okay, so 1/3 arcsine of 3x plus c. So just be on guard. A couple of the homework problems, if the first substitution you try doesn't work, maybe see if you can figure out how to twist the denominator of an expression like this or the one before into something like one of those derivatives of the inverse trig functions. So keep that in mind. Achievement unlocked. We've covered all of our course material for the semester. So I plan on posting some videos based on sort of a course and review thing related to some review problems that'll be going up later on. But for now, rest on your laurels. We've finished everything, at least as far as videos go. Yay!